Ever get that feeling like you're on the verge of something big and totally new? That's kind of how I feel about today's topic. Quantum materials.
Yeah.
They sound straight out of sci-fi.
Right.
But they're very real, and we're only beginning to understand what we can do with them.
Absolutely.
These are solids, like the stuff we see every day, but instead of just their atoms interacting with normal physics, these materials are governed by quantum mechanics.
Exactly. And that's where it gets really interesting, because the rules of quantum mechanics are so different from what we experience in our everyday world.
It's almost like the quantum realm, usually confined to the tiny world of atoms, is suddenly writ large.
Yeah, exactly. You could hold a quantum material in your hand, and macroscopic properties are directly determined by these quantum effects.
Like we're talking about things like electrons behaving as waves.
Yes.
Existing in multiple states at once.
Superposition.
Superposition, yeah.
Entanglement, where particles are linked across distances.
Spooky action at a distance.
Yeah, all this stuff.
All this stuff that seems so weird and counterintuitive.
Yeah, but it's happening in these materials.
It's what gives them their amazing properties.
Absolutely.
So before we dive into the specifics, I just want to mention the essay that really inspired this deep dive. Quantum Materialien. Innovation for Technologien der Zukunft by Jorgo Schneeppert.
A great piece. Really lays out the landscape.
Yeah, Schneeppert does a great job of highlighting the key concepts and the potential of these materials.
Totally. And I think what's really exciting is that we're only at the beginning of exploring this field.
Right. Our mission today is to really pull out the most fascinating nuggets from Schneeppert's work.
Yes.
See what these materials can do and what they could mean for our future.
Absolutely. So where do you want to start?
Well, I think it helps to understand where this all began.
Okay.
So let's rewind a bit.
Yeah.
Back to the early 20th century, the birth of quantum mechanics.
Right, the revolution in physics.
It's like this completely new way of thinking about the universe, and it turns out it's the key to understanding these quantum materials.
So without quantum mechanics, we wouldn't even know where to begin.
And Schneeppert reminds us about one of the earliest and most mind-blowing discoveries in this field, superconductivity.
Ah, yes. 1911, Heick-Kamerlingh ohms.
Right.
Cooling down mercury to just a few degrees above absolute zero.
Imagine mercury, that liquid metal we all know.
Yeah.
Suddenly has zero electrical resistance.
No resistance whatsoever.
Electricity just flows through it without any loss.
It defied explanation for decades.
It's like something out of a science fiction novel.
People were baffled.
So how did they finally crack the code?
Well, it took almost 50 years.
Wow.
Until 1957.
Okay.
When three brilliant physicists, John Bardeen, Leon Cooper, and John Schrieffer, came up with what we now call the BCS theory.
BCS.
Yeah, and this theory showed that in certain materials, at very low temperatures, electrons can actually pair up.
Pair up?
Yes, they form these Cooper pairs.
Cooper pairs.
And these pairs can move through the material's lattice without any scattering.
Like a perfectly synchronized dance.
Exactly. And that's what leads to zero resistance.
And the BCS equation, it helps us understand the temperature at which this happens.
It relates the critical temperature to properties of the material, like how the atoms vibrate, the energy of the electron.
It's amazing how seemingly unrelated things can lead to such a profound effect.
It really is.
So we have superconductivity, but the story doesn't end there.
No, not at all.
Schneeppert talks about another major breakthrough in 1986.
Okay.
High-temperature superconductivity.
Yeah, this was huge.
Bednorz and Miller discovered materials that could superconduct at temperatures way higher than anyone thought possible.
Like above 100 Kelvin?
Still incredibly cold, but you could use liquid nitrogen to cool them down.
Which is way more practical than liquid helium.
So much cheaper and easier to work with.
Yeah, suddenly superconductivity seemed much closer to real-world applications.
But here's the twist. The BCS theory, which explained traditional superconductivity, doesn't fully account for this high-temperature phenomenon.
That's right.
It's still a mystery, a huge area of active research.
And a very exciting one. It tells us there's still so much we don't understand about these materials.
So we've got superconductivity, both the traditional kind and this high-temperature kind.
Yes.
But Schneeppert also introduces us to some other fascinating quantum materials like topological insulators and wire semiconductors.
Right. These came onto the scene more recently.
Yeah, early 2000s.
And they really blew people's minds.
What's so special about them?
Well, imagine a material that's an insulator on the inside.
Like it doesn't conduct electricity?
Exactly.
Okay.
But then on its surface or its edges, it's incredibly conductive.
It's like a hidden highway for electrons.
Yeah, that's a great analogy. And what's even more remarkable is that these conducting states are extremely robust.
Robust?
Yeah, they're protected by the topology of the material.
Topology.
It's a mathematical concept that describes the shape and connectivity of something.
Okay.
And in these materials, the topology of their electronic structure makes these surface states incredibly resistant to disruptions.
So impurities or defects don't affect them?
Not easily, no.
It's like they have this built-in shield.
Yeah, and this robustness makes them really attractive for potential applications.
So we've got these mind-bending materials, but how do scientists actually study them? How do we peer into this quantum world?
Well, Schneeppert points out that advances in experimental techniques have been absolutely crucial.
Yeah.
Like without the right tools, we'd be completely in the dark.
So what are some of the key techniques?
Well, one that we've already mentioned is scanning tunneling microscopy, or STM. It's like a super-powered microscope that can image surfaces at the atomic level.
Atomic level.
Yeah, it uses a tiny, incredibly sharp tip to measure a current that tunnels between the tip and the sample.
Okay.
And the strength of that current tells us about the electron wave functions at that specific point.
So it's like feeling the surface of the material with a single atom?
Yeah, pretty much.
Incredible. What else?
Another powerful technique is using synchrotron radiation.
Okay.
Which is basically incredibly bright, focused light that can be used to probe the structure and behavior of electrons in these materials.
So like shining a super powerful flashlight into the quantum world.
Exactly. And by analyzing how the light interacts with the material, we can learn a ton about its properties.
So with these tools and many others, scientists are starting to unravel the secrets of quantum materials.
Yeah, it's like a whole new world opening up.
But Schneeppert makes it clear that these aren't just curiosities for physicists.
No, not at all.
They have huge implications for science, technology, and society. So let's talk about their significance.
Okay.
First, from a scientific perspective.
Yeah.
Quantum materials offer a unique window into the fundamental workings of quantum mechanics.
That's right.
Like how electrons interact with each other, how they maintain their quantum coherence.
Yeah, these are things that are really hard to study in other systems.
So they're like a testing ground for our understanding of the quantum world.
Absolutely.
Yeah.
And we're seeing phenomena that were previously just theoretical ideas.
Like what?
Well, things like spin liquids.
Spin liquids?
Yeah, it's a state of matter where the spins of the electrons are constantly fluctuating.
Like a quantum dance party.
Yeah, something like that. And these exotic states can only exist because of the quantum nature of these materials.
It's mind-blowing. So they're helping us unlock deeper secrets of the quantum world?
Totally.
But what about their impact on our lives?
Well, Schneeppert talks about a wide range of potential technological applications.
Yeah.
And some of them are already becoming reality. Well, we've talked about superconductivity. And those superconducting magnets are already used in MRI machines.
In hospitals.
Yeah, and in particle accelerators like the Large Hadron Collider.
Amazing. What about future applications?
Well, Schneeppert mentions superconducting power grids.
Yeah, where electricity could flow without any loss.
Exactly. That would be a huge step towards a more sustainable energy future.
Imagine, no more wasted energy in transmission lines.
Yeah.
And then there's quantum computers, which rely heavily on the properties of quantum materials. It's amazing to think that these strange quantum phenomena could lead to such revolutionary technologies.
It really is.
And Schneeppert doesn't shy away from the societal implications either.
No, it's important to consider the broader impact.
Yeah, like these technologies could lead to incredible advances in energy efficiency and resource utilization.
Absolutely.
But we also need to think about access and potential inequalities.
Yeah, who benefits from these technologies?
Right.
Who might be left behind?
It's a crucial reminder that scientific progress needs to be accompanied by careful consideration of its ethical and social dimensions.
Absolutely. We need to ensure that these advancements benefit all of humanity.
So we've talked about the significance, the history, but let's delve a little deeper into what makes these quantum materials tick.
Okay.
What are the fundamental quantum properties that Schneeppert describes?
Well, it all starts with the quantum nature of electrons.
Right, electrons, those tiny particles that are responsible for electricity.
Exactly. But in quantum materials, we have to think about electrons in a very different way.
Different how?
Well, in classical physics, we think of electrons as particles.
Like tiny balls of charge?
Yeah.
Okay.
But in quantum mechanics, electrons also have wave-like properties.
Wave-like?
Yeah, it's called wave-particle duality.
So an electron can be both a particle and a wave.
Exactly.
Yeah.
And this duality is absolutely crucial for understanding how these materials work.
It's like they have this dual nature, switching between particle and wave, depending on the situation.
Yeah, it's mind-bending. And this wave-like nature means that we describe electrons in these materials using wave functions.
Wave functions?
Yeah, they're mathematical expressions that describe the probability of finding an electron at a particular point in space.
Okay.
And the behavior of these wave functions is governed by the Schrödinger equation.
The Schrödinger equation.
Yeah, it's one of the fundamental equations of quantum mechanics.
So this equation tells us how the electron waves move and evolve over time.
Exactly. And it explains why electrons in solids can only exist in specific, discrete energy levels.
Like rungs on a ladder.
Yeah, that's a good way to visualize it. And this quantization of energy is essential for understanding the properties of these materials.
So it's not just about the electrons themselves, it's also about how their wave-like nature leads to these quantized energy levels.
Absolutely.
And then there are these even weirder quantum concepts.
Oh, yeah.
Like superposition and entanglement.
Those are the real head-scratchers.
Schneepat talks about these.
He does, and they're crucial for understanding some of the most bizarre phenomena in these materials.
So let's start with superposition.
Yeah.
What does that even mean?
Well, in the quantum world, particles can exist in multiple states at the same time.
Multiple states?
Yeah, like an electron can be spinning both up and down simultaneously.
It's like it's in two places at once.
Or two states at once, yeah. And this superposition principle is what allows for those coherent states that are so important for superconductivity and other quantum phenomena.
So it's like the electron is a blur of possibilities.
Yeah, until we measure it.
And then it collapses into a single state.
Exactly. It's like the act of observation forces it to choose.
It's so weird.
It is, but it's the way the quantum world works.
And then there's entanglement.
Ah, entanglement.
This is the one that Einstein called spooky action at a distance.
He did. And it's probably the most mind-boggling concept in quantum mechanics.
So what is it?
Well, it's when two or more particles become linked.
Linked?
Yeah, their properties become correlated.
Okay.
Even if they're physically separated.
Separated by a huge distance.
Yeah, it doesn't matter how far apart they are.
So if you measure the state of one particle, you instantly know the state of the other.
Exactly. It's like they're communicating faster than the speed of light.
Yeah, but they're not actually communicating, right?
No, it's not that they're sending signals back and forth.
So how does it work?
Honestly, we don't fully understand it.
It's just a fundamental feature of the quantum world.
Yeah, and it plays a crucial role in explaining collective behaviors in quantum materials.
Like those spin liquids we talked about.
Exactly. The entanglement between the electron spins is what allows them to form these exotic states.
It's like they're all connected in some invisible way.
Yeah, and this interconnectedness is what gives these materials their unique properties.
So we've got this whole zoo of quantum materials, each with its own set of bizarre quantum properties.
Mm-hmm.
But Schneepat offers a way to classify them, to make sense of this diversity.
He does.
So what are the main categories he discusses?
Well, he focuses on four main classes.
Okay.
First, we have the superconductors, which we've already talked about quite a bit.
Zero resistance, Cooper pairs, the whole deal.
Exactly. Then there are the topological insulators, with their conducting surfaces and insulating interiors.
Those protected electron highways?
Yeah. And then we have quantum magnets.
Quantum magnets.
Yeah, these are materials where quantum mechanics plays a dominant role in their magnetic properties.
So their magnetism is different from ordinary magnets.
Yeah, they can exhibit really unusual magnetic arrangements and behaviors.
Like what?
Well, things like spin liquids.
Those again.
Yeah, they pop up everywhere in quantum magnetism.
And finally, we have Dirac and Weil semiconductors.
These are the speed demons of the quantum material world.
What do you mean?
Well, the electrons in these materials behave as if they have no mass.
No mass.
Yeah, and that means they can move at incredibly high speeds.
Approaching the speed of light.
Well, not quite that fast, but much faster than electrons in ordinary materials.
So it's like they're zipping around at relativistic speeds.
Yeah, and this gives them some really unique properties that are very attractive for potential applications.
So we've got these four main classes, each with its own set of quantum quirks.
Exactly.
And we've talked about the tools scientists use to study them. But Schneepat also delves into some of the innovative applications of these materials, and he starts with superconductivity.
Makes sense. It's one of the most well-established and exciting areas.
Right. We've already talked about the use of superconducting magnets in MRI machines and particle accelerators.
Yeah.
But Schneepat also highlights the potential for superconducting power grids.
Yeah, imagine transmitting electricity over vast distances with no energy loss.
That would be a game changer for our energy infrastructure.
Absolutely. It would make our grids much more efficient and reduce our reliance on fossil fuels.
And then there's the potential for superconductivity in quantum computing.
Yeah, superconducting circuits are one of the leading platforms for building quantum computers.
It's incredible to think that something discovered over a century ago
I know, right?
could be so central to the future of technology.
It really shows the power of fundamental research.
So superconductivity is a big deal.
Definitely.
But Schneepat also explores the potential of those other classes of materials.
He does.
Like, what about topological insulators?
Ah, yeah, those robust surface states.
Right.
Well, Schneepat sees huge potential for them in spintronics.
Spintronics.
Yeah, it's a field that aims to use the spin of electrons to carry information.
Instead of their charge.
Exactly. And this could lead to much more energy-efficient electronics.
Why is that?
Well, manipulating spin requires much less energy than moving charge around.
So we could have devices that last much longer on a single charge.
Yeah, potentially. And Schneepat mentions the spin Hall effect, which allows us to generate spin currents without any net flow of charge.
So we could control the spin of electrons without actually moving them.
Yeah, and that opens up all sorts of possibilities for information processing and storage.
And because those topological states are so robust, these spintronic devices could be much more reliable and resistant to errors.
Exactly. They could operate in harsher environments and last much longer.
It's like building electronics with quantum armor.
Yeah, I like that.
So what about those quantum magnets? Schneepat talks about some really interesting applications there, too.
He does, like those tiny magnetic vortices. Skyrmions?
Skyrmion?
Yeah, Schneepat suggests they could be used for ultra-high-density data storage.
Like storing more information in a smaller space.
Exactly. And they're also very energy efficient.
So we could have smaller, faster, more efficient memory devices.
That's the idea.
And Schneepat also mentions the potential for spin-based quantum logic gates.
Yeah, this is getting into the realm of quantum computing again.
Right.
By controlling the spins of electrons in quantum magnets.
Yeah.
We could potentially create the building blocks for a new type of quantum computer.
It's amazing how all these different quantum phenomena
I know, right?
are converging towards this goal of building a quantum computer.
It really shows the interconnectedness of this field.
So finally, we have the Dirac-and-Weil semiconductors.
The speedsters.
Schneepat seems pretty excited about their potential for new forms of electronics.
He is. And for good reason.
Like, what kind of applications are we talking about?
Well, their high-charge carrier mobility.
Remember, those massless electrons zipping around.
Exactly. That could lead to much faster and more energy-efficient transistors.
The fundamental building blocks of our electronics.
Exactly. Imagine computers and smartphones that are orders of magnitude faster and use a fraction of the energy.
That would be revolutionary.
Yeah. And Schneepat also points out their potential in photonics.
Photonics?
Yeah, the science of light.
Okay.
These materials can interact with light in very unusual ways.
Okay.
Which could lead to new types of optical devices, faster data transfer, even applications in quantum cryptography.
It's incredible to think that we're just scratching the surface of what these materials can do.
Yeah, the possibilities seem endless.
But, as with any cutting-edge research, there are also challenges.
Absolutely. Schneepat doesn't shy away from the difficulties.
So what are some of the hurdles that we need to overcome?
Well, one of the biggest is simply synthesizing and manufacturing these materials.
Like actually creating them in the lab?
Yeah, many of these materials are incredibly complex.
Okay.
With very specific structures and compositions.
So it's not easy to just whip them up?
No. It requires incredibly precise control over the growth process.
What kind of techniques are used?
Well, Schneepat mentions molecular beam epitaxy, or MBE.
MB.
Yeah, and chemical vapor deposition, or CVD.
CVD.
These are techniques that allow us to grow thin films with atomic precision.
Atomic precision.
Yeah, but scaling these techniques up to produce large quantities of material with consistent quality.
Right, for industrial applications.
That's a major challenge.
So we can make these amazing things in small batches, but making them reliably and at scale is still a hurdle.
Yeah, and that's a common problem in material science.
Makes sense.
Taking something from the lab to the factory is often the hardest part.
What about theoretical challenges?
Well, Schneeppert talks about the difficulty of understanding complex phase transitions.
Like how a material changes from one state to another.
Exactly. Like how does a metal become a superconductor when you cool it down?
Okay.
These transitions are often driven by incredibly complex interactions between many electrons.
So it's not just about the individual particles, it's about how they all behave collectively.
Exactly.
Yeah.
And that's really hard to model theoretically.
What kind of theoretical approaches are used?
Well, Schneeppert mentions density functional theory, or DFT.
DFT.
It's a very powerful tool.
Okay.
But even DFT has its limitations when it comes to these strongly correlated systems.
Strongly correlated.
Yeah, it means that the electrons are all pushing and pulling on each other,
Okay.
and their behavior's very intertwined.
So it's like a giant quantum dance party where everyone is stepping on each other's toes.
Yeah, something like that.
So we've got these synthesis challenges, these theoretical challenges, but despite these hurdles, the future of quantum materials research seems incredibly bright.
Oh, absolutely.
What are some of the future directions that Schneeppert outlines?
Well, he sees a lot of potential in energy technologies,
Okay.
like using quantum materials to develop better batteries.
Batteries.
Yeah, batteries that can store more energy, charge faster, and last longer.
That would be huge.
It would. And he also talks about thermoelectric materials.
Thermoelectric.
Yeah, these materials can convert heat into electricity.
Like capturing waste heat and turning it into usable energy?
Exactly.
That would be amazing for sustainability.
It would.
Yeah.
And imagine we could use them to power sensors and other devices in remote locations.
So quantum materials could play a key role in a more sustainable energy future.
Absolutely.
And what about their role in quantum technologies?
Well, we've already talked about their potential in quantum computing.
Right, superconducting circuits, spin-based qubits.
Yeah, and Schneeppert also mentions their potential in quantum communication.
Quantum communication.
Yeah, using quantum properties to transmit information securely.
So unhackable communication.
That's the idea.
It's like something out of a spy movie.
It is. And these quantum materials could be the key to making it a reality.
And finally, Schneeppert talks about the importance of interdisciplinary research.
Yeah, this is a field that requires expertise from many different areas.
Like physics, chemistry, material science.
Exactly. And even computer science and engineering.
So it's a truly collaborative effort.
It has to be.
What are some of the exciting new areas that are emerging?
Well, Schneeppert mentions the intersection of quantum materials with biotechnology.
Biotechnology.
Yeah, using these materials to create new types of biosensors, bioelectronic interfaces.
Like merging the quantum world with the biological world.
Exactly. And he also talks about the development of hybrid quantum systems.
Hybrid systems.
Yeah, combining different quantum materials together to create even more exotic properties.
So it's like building with quantum Legos.
Yeah, something like that.
It's incredible to think about all the possibilities that are opening up.
It really is. And it's important to remember that this is still a relatively young field.
Right. We're just at the beginning.
So who knows what amazing discoveries are yet to come.
It's so exciting. So to wrap up our deep dive,
Okay.
let's recap the key insights from Yorgo Schneeppert's essay.
He really lays out a compelling vision for the future of quantum materials.
He does. So what are the main takeaways?
Well, I think the biggest one is that quantum materials are truly a new frontier in material science.
Yeah, they're not just an incremental improvement.
No, they represent a fundamental shift in how we think about and design materials.
It's like we're moving from the classical world to the quantum world.
Exactly. And this shift is driven by our increasing ability to control and manipulate matter at the quantum level.
And this is leading to breakthroughs in a wide range of fields.
Absolutely. We've talked about energy, electronics, quantum technologies.
And even medicine and biotechnology.
Yeah, the potential applications are vast and incredibly exciting.
But Schneeppert also acknowledges the challenges.
He does.
The difficulties in synthesis, the theoretical complexities.
But he's ultimately optimistic about the future.
Yeah, he sees quantum materials as a key driver of scientific and technological progress.
He does.
And he calls for increased investment in research and collaboration.
Yeah, he emphasizes the importance of bringing together scientists from different disciplines
to tackle these challenges and unlock the full potential of these materials.
Absolutely.
So I think we've covered a lot of ground today.
We have.
And your Goshnepit's essay has given us a fantastic overview of this exciting and rapidly evolving field.
Totally agree.
It really makes you wonder, what's next? What unexpected applications might emerge in the coming years?
Yeah, that's the big question.
It's truly a fascinating time to be following this field.
I couldn't agree more.
So thank you for joining us on this deep dive into quantum materials.
It was my pleasure.
And to our listeners, keep exploring, keep asking questions.
Yeah, stay curious.
Because the quantum world is full of surprises. And who knows what amazing discoveries await us just around the corner.
Absolutely.